Welcome to Mutlu Learning Hub. In this video, we are going to talk about logistic regression, one of the simplest and most important models for classification. The key idea is this: how do we take inputs and turn them into probabilities? Logistic regression starts with a linear score and then transforms it into something between 0 and 1. By the end, you'll understand how it works, why it works, and when to use it. Here is the plan for today. First, we'll understand the problem logistic regression solves. Then, we'll see why linear regression is not enough. After that, we'll turn scores into probabilities and decisions. We'll briefly look at how the model is trained. And finally, how to interpret and evaluate it. Let's start with the problem. Unlike regression, here we are not predicting numbers, we are predicting categories. For example, is an email spam or not? Will a customer default or not? Does a patient have a disease or not? So instead of continuous outputs, we want discrete labels. And the goal is to separate these classes, ideally with a clear boundary, like you see in this image. Here, this line is our decision boundary. If we have a point on the right, we say it's class 1. And if we have a point on the left, we say it's class 0. Let's see what happens if we try to use linear regression. We have two classes, 0 and 1, and we try to fit a straight line. But here is the problem. A straight line does not respect probabilities. It can go below 0 or above 1, and probabilities must always stay between 0 and 1. So this approach breaks down. Let's see what happens if we try to use linear regression. We have two classes, 0 and 1, and we try to fit a straight line. But a linear model does not naturally enforce that. So we need a way to keep the simplicity of linear models while forcing the output into the probability range. That's exactly where logistic regression comes in. The idea is actually very elegant. First, we compute a linear score, just like in linear regression, a weighted sum of the inputs. Then we pass that score through a function that turns it into a probability. That function is called the sigmoid. So, input, score, and then probability. The sigmoid function is the key. It takes any real number, no matter how large or small, and maps it into a value between 0 and 1. Here is the sigmoid function. You can see that if the score is very negative, the probability is close to 0. If the score is very positive, it's close to 1. And if the score is around 0, the probability is about 0.5. So now we have valid probabilities. But probabilities alone are not enough. We need to make a decision. So we choose a threshold, usually 0.5. If the probability is above the threshold, we predict class 1. If it's below, we predict class 0. And importantly, this threshold is flexible. You can adjust it depending on the problem. Now, here is something interesting. The decision boundary is still linear. Why? Because the threshold corresponds to the score being 0. So even though we use a nonlinear function, the sigmoid, the boundary itself, is still linear. For example, if we have only one feature, the boundary is a cutoff point. If we have two features, the boundary is a line. With more features, the boundary is a hyperplane. That's why logistic regression is still considered a linear model. So, how does the model learn? It tries different coefficients. Each choice gives different probability. Some match the data better than others. So we need a way to measure how good or bad our prediction. That's where the loss function comes in. For a single prediction, we use something called log loss. It penalizes wrong predictions, especially confident wrong ones. Then we average this over the whole dataset to get the cost function. Training means find the best coefficients that minimize this cost. So we are basically searching for the best coefficient. Is how do we find this best fit? By the way, there is also an important mathematical reason we use log loss. When we combine the sigmoid with log loss, the cost function becomes convex. That means it has a single global minimum. In other words, training becomes much more reliable. To minimize the cost, we use gradient descent. We start with an initial guess, then we compute the gradient, the direction where the cost increases the most, and we move in the opposite direction. Step by step, we move downhill until we reach a minimum. That's how the model learns its parameters. Once the model is trained, we evaluate it. A simple metric is accuracy, the fraction of correct predictions. To compute it, we first convert probabilities into class labels, then compare them with the true labels. But keep in mind, accuracy can be misleading when the classes are imbalanced. What do the coefficients mean? They tell us how each feature affects the prediction. A positive coefficient pushes the score and probability up. A negative coefficient pushes it down, and the larger the magnitude, the stronger the effect. So, logistic regression is actually quite interpretable. Logistic regression works especially well when you want a simple and interpretable model. You're working with tabular data, you need a strong baseline, and the boundary is roughly linear. It's often one of the best first models to try. But it's not perfect. It struggles with complex nonlinear relationships, it can miss interactions between features, and it may underperform when the true boundary is complicated. At the end of the day, it's still a linear model. Here is the big picture. Logistic regression starts with a linear score, turns it into a probability, and uses a simple rule to classify. That's why it's simple, interpretable, and still very powerful. Thanks for watching. If this helped, feel free to like and subscribe, and I'll see you in the next video.